All right. All right. Welcome, everybody, to another exciting session of CE 397, Control Theory for Smart Infrastructure. Last time, we covered some core concepts from linear algebra. We kind of covered them at maybe a more theoretical level than you've looked at in the past. So we talked about span. We talked about linear independence, bases, and then we moved on to a couple of concepts for characterizing vectors and vector spaces. We talked about norms and we talked about inner products. So just to quickly recap, who wants to tell me what the span of a set of vectors is? Just really quick. I don't want to call out. What's the span of a set of vectors? Yeah, so it's the collection of all the vectors that a set of vectors can reach if you scale those vectors and add them together. Great, so that's exactly right. What about linear independence? What makes a set of vectors linearly independent or linearly dependent? Let's just quickly call out here.
A linear combination of those vectors and not sum to zero, then it's linear.
Yes, that's exactly correct. So if you cannot find a set of coefficients alpha such that if you scaled your vectors by those coefficients alpha and add them together to produce the zero vector, that set of vectors is linearly independent. So we'll talk a little bit more about linear independence today. And then we also talked about bases. So who quickly wants to just recap what a basis for a vector space is? What does a basis allow us to do? Yeah, so it's a collection of vectors in a vector space that is linearly independent and what else? And it spans the subspace. Oh, spans the vector space. Yes. So what does that allow us to do with the basis? Yeah, it means we can represent any vector in that vector space using a linear combination of those bases. Of those basis vectors. So that's effectively what a basis allows us to do. So great, you got all of the definitions down. Great. After that, we talked a bit about norms and inner products. So we wanted to talk about ways that we can characterize the size of vectors in a vector space and their orientation to one another. So we talked about norms. We talked about some familiar ones like the Euclidean norms, and then we introduced some new norms that you may not have seen before, such as the infinity norm, and several matrix norms. Has anyone got a favorite norm that we talked about yesterday or last week? Anyone have a favorite norm? Right. Well, I mean, if push comes to shove, you got to choose. I like the two norm. It's it's familiar. It's always there for you when you need it. So yeah, so we talked about norms, inner products, and we provided formal definitions for those concepts. Today, we're going to finish up our discussion from last time. We're going to talk about orthogonality of vectors. We're going to talk about the orthogonal complement of a vector space. This is going to be important later on when we talk about the four fundamental subspaces and controllability and observability of dynamical systems. And finally, we're going to talk a bit about linear transformations, just generally what they are and how we can represent any linear transformation as a matrix. All right, are there any questions on anything we covered last time before we move on? Any questions? All right, well, let's continue. So the first thing I want to talk about today, just finishing up what we were talking about last time with inner products, is I want to talk about orthogonality of vectors. So this is something that may be familiar to you from undergraduate linear algebra. If we have two vectors, u and v, so let u and v be two vectors in a vector space with a valid inner product. Okay, so it has to meet the definition of the inner product that we gave last time. Then we say that u and v are orthogonal if the following equation holds. If we take the inner product of u with v, that inner product is equal to 0. Okay, so we say that u and v are orthogonal if their inner product in some vector space with a valid inner product is equal to 0. Right? We also say that those vectors are orthonormal. So they're orthonormal if we take that same inner product u and v, and if u is not equal to v, that inner product is equal to 0. And if u is equal to v, i.e., we take the inner product of u with itself or v with itself, we get 1. Okay, so it's a set of two vectors is orthonormal if each vector is unit norm and is orthogonal with the other vector. Okay, so let's go through a couple examples of vectors that are orthogonal and or orthonormal. Okay, let's take a look at two vectors. U is equal to 2, 1, and v is equal to 1, -2. And let's just say for completeness, u and v are in R2. Okay, so we're in the vector space of two-dimensional real valued vectors. Okay, so are these vectors orthogonal to one another? We can see that they are. So if we take u transpose v, so this is the inner product of u with v, we get 2, 1, inner product of 1, -2. This gives us 2 times 1 plus 1 times -2, which we see is equal to 0. Are these vectors orthonormal? No, they're not orthonormal. Why is that? Because they're not unit norm, right? So if we take the norm of u, for instance, let's just say, let's look at the norm squared. So that will be u transpose u. We'll get 2, 1, inner product with 2, 1. And that will give us 4 plus 1 is equal to 5. Okay, so the norm of u will actually be square root of 5. So this set of vectors is orthogonal, but not orthonormal. All right, let's take a look at another example. Let's just look at a set of vectors. Let's say u is equal to the following family of vectors: cosine theta, sine theta. And let's say v is equal to the following set of vectors: negative sine theta, cosine theta. Okay. Is this set of vectors orthogonal?
Yes.
Yes. How do we know that? Let's say we take u transpose v. So we will get cosine theta, sine theta, inner product with negative sine theta, cosine theta, which gives us cosine theta, negative sine theta, plus sine theta, cosine theta. Okay. And you can see that this will equal 0, right? Okay, are these vectors orthonormal to one another? Jimmy is saying yes. So we can confirm that they are also orthonormal, meaning that each one is unit norm. So let's take the norm of u, and let's just look at the norm of u squared. If we look at the norm of u squared, we have that this is equal to u transpose u, which is equal to cosine theta, sine theta, inner product with cosine theta, sine theta. This will give us cosine squared of theta plus sine squared of theta. And from trigonometry, we know that this is equal to 1, right? This is equal to 1. This is the norm squared. If we take the square root, we still get that it's equal to 1. Okay, so this set of vectors is orthogonal and unit norm for any theta. So this is a special, yes.
So we use the 2 norm here. Is that just the definition of orthogonality? Because the 1 norm, it looks like it would not be unit.
Let me check. I think it has to do with your definition of the inner product. I can check on that. That's a good question. But as far as I know, yes, it does have to be the 2 norm. And I think it has to do with the definition of the inner product that is used here. So in this case, our inner product space. So just to note, a vector space with an inner product defined is called an inner product space. That's what we're dealing with when we're talking about orthonormality. And I can check on that, but I believe that the definition of the inner product we use necessitates that we also have to use the 2 norm. Yeah. Okay, good question. All right. Okay, one more example for you. Let's say that we are in the vector space. Let's say where u and v are in C2, vector space of complex valued 2-dimensional vectors. And let's say that our inner product, the inner product of u with v is defined as u Hermitian transpose v. Okay, so this is a valid inner product for this vector space. And let's say that our vectors are let's say u is equal to 1j and v is equal to 1 negative j. So are these orthogonal to one another? So I'll give you about 30 seconds to check. And let me know if you think these are orthogonal to one another. Okay, so I'm seeing a couple nods. So let's go ahead and take the inner product of u with v, which is equal to u Hermitian transpose v. Okay, what does u Hermitian transpose become? We have 1 and what's the second element? Negative j, right? If we're taking the Hermitian transpose, we have to take the complex conjugate of every element. Okay, we take the inner product with 1 negative j. And what we should get is 1 times 1 plus negative j times negative j. And this is equal to 1 plus negative 1 times negative 1. Is that right? 2. Did I mess up my math thing? Oh, sorry. You are right. Yes, negative. Yes, there we go. So this should actually end up being.
It should be on J square. it should be -2 times -a, which is plus a squared. Yes.
Which is -1. Okay, thank you. So you'll end up with 1 minus 1, which is equal to 0. Thank you. Yes, and this should be -j, -j. There you go. All right. Thank you for helping me through that problem. So we can see that these two vectors are orthogonal. This is just to show to you that when you are working with complex valued vectors, generally your inner product will be defined in this way. And so you need to remember to take the conjugate transpose when you're looking for whether they're orthogonal or not. Okay. Are there any questions on this example? Okay, so next I want to give you just a quick overview of unitary and orthogonal matrices. So who's heard the term unitary matrix before? Okay. Who's heard the term orthogonal matrix before? Okay, so some of you here. So a unitary matrix is basically just a generalization of a orthogonal matrix for complex valued vector spaces. So a unitary matrix is a square matrix whose columns and rows are orthogonal unit vectors. So in other words, A is, let's say, a matrix A is unitary if and only if A Hermitian transpose A is equal to A Hermitian transpose is equal to the identity matrix. All right. And note that if we are in a real valued vector space, this reduces to A transpose A is equal to A transpose is equal to the identity matrix. All right. What does this also imply about A and A Hermitian transpose and their relation to one another? Right. So A and A Hermitian transpose are inverses of one another by the definition of the inverse, right? If you take A times A inverse, you should get the identity matrix, right? So in other words, if a matrix is unitary, its Hermitian transpose is also its inverse. All right, so let's go through a couple quick examples. Probably the most simple example of a unitary matrix is the identity matrix. Okay, we can see that I transpose I is equal to I transpose is equal to I. Okay, so the identity matrix is a unitary matrix. Another unitary matrix are, so another set of unitary matrices are matrices of the following form: cosine theta, negative sine theta, sine theta, cosine theta. Okay, so these are called rotation matrices. You'll see these a lot in physical problems where you are rotating some set of vectors. They appear a lot in graphics as well. But we know from before that we have that this is equal to our vectors u and v, right, from before, and that u and v are orthonormal, meaning that if you take A transpose A, you will get the identity matrix, right? Because we showed that U is orthogonal to V and that U is unit norm and V is unit norm. Okay, so when you take the inner product, when you take A transpose A, you'll get inner product of U with U, inner product of V with V, inner product of U with V, and inner product of V with U, which gives you the identity matrix. Okay, so rotation matrices are unitary or orthogonal for any value of theta. All right. Are there any questions on unitary matrices, orthogonal matrices, or just orthogonality in general? Right. I know I've been hitting you with a lot of definitions, but we're going to need them later on, so I want to make sure I get them out of the way. All right. Now, sometimes in control problems or just in linear algebra problems in general, we'll have a basis for a vector space or a basis for a subspace of a vector space, and we want to find a set of vectors that can complete our basis for the entire vector space. So we may have a basis for just one subspace of a vector space, and we need another set of bases to complete our basis for the entire vector space. So one important way to do that is to find what's called the orthogonal complement of a vector space. So I'm going to talk about this notion of the orthogonal complement. It's going to be really important later when we start talking about the four fundamental subspaces. So this is an important concept to remember. It also comes up a lot in just the field of signal processing in general. So let's say we have some vector space, V. Let V be a vector space. And let R and S be subspaces of that vector space. Okay, so we have a vector space V. We have R and S, which are subspaces of V. Then we say that the intersection of R and S, our two subspaces, is given by R intersection with S and is the set of vectors that is shared between R and S. So it's the set of vectors such that V is in R and V is also in S. Okay. We can also define the notion of a sum of two vector spaces. Okay, so we say that the sum of R and S is denoted as R plus S. So note that these are vector spaces, so these are sets. The sum of R and S is equal to R plus S. So I'll define what R and S are in a second. So it's R plus S for all R in our vector space R and S in our vector space S. So if we take all of the elements from R and we add them together with all of the elements from S, so we take a vector from R, we add it with some other vector from S, we take another vector from R, we add it with some other vector for S, and we find all of the combinations of the sums of the vectors from R and S. That gives us the sum of R and S. Okay, note that this is not the same as the union of R and S. So the union is the set of vectors that are either in R or in S. If we're talking about the sum of R and S, what we're actually talking about is the shared span of R and S. So if you take the vectors from R and you add them together with all the different vectors from S, you'll get the shared span of those two vector spaces. So you're literally adding the vectors together. Okay. Are there any questions on this notion of the sum of a vector space? I know it can be a bit difficult to think about, but you can think about it as being the shared span of your subspaces R and S. Okay, so we've defined the intersection and the sum of two subspaces. We can also define what's called the direct sum. So we'll say that T, this is a new vector space, is the direct sum of R and S. And it is the direct sum of R and S if, one, the intersection of R and S is 0. In other words, there are no vectors that are shared between R and S. Okay, so R and S contain no common vectors. And 2, the sum of R and S is equal to T. In other words, the shared span of your subspaces R and S are equal to your larger vector space T. Okay, so R and S together span all of T. Okay, so in this case, R and S are said to be complements of each other in T. So to recap, R and S are said to be complements of one another in T if there are no shared vectors between R and S, and if you can reconstruct any vector in T uniquely as a combination of vectors in R and S. Okay, and I will write that down because it's important. If T is equal to the direct sum of R and S, if R and S, in other words, are complements of each other in T, then every T, every vector T in our larger vector space T can be written uniquely in the form T equals R plus S with little r in big R and little s in big S. In other words, if they're complements of each other, then every vector in our vector space can be written as a unique linear combination of a vector from our subspace R and from our subspace S. So in other words, we've partitioned the vector space T into two complements of one another that span the entire vector space T. Okay, so note that the set of complements, the complement of R is not necessarily unique, and the complement of S is not necessarily unique, but there is one unique complement for R that is useful for our purposes. So there's one unique complement of R that is, I'll say, especially useful. And that is called the orthogonal complement. So I'll move on to the next page here. Okay, so the orthogonal complement. So let's define it as follows. Let R be subspace of Rn, so the vector space of n-dimensional real valued vectors. Then the orthogonal complement is the set of vectors in Rn that are orthogonal to every vector in R. So we can define that as follows. We define it as R with this kind of little perpendicular symbol. It is equal to the set of vectors in Rn such that V transpose U is equal to 0 for all U in, for all U in R, our subspace. So what this allows us to do is, if we have a subspace of a vector space, we can find a unique complement to that subspace such that we can reconstruct any vector in the larger vector space. And again, those vectors can be constructed uniquely. So this is going to be really important later on. So let me give you one intuitive example of an orthogonal complement. So let's say we have our vector space, our larger vector space V is R3. And we have some subspace R, which is equal to the span of the vectors 1, 0, 0, and 0, 0, 1. Okay, what is our orthogonal complement? What is our orthogonal complement to this subspace? So first of all, how many bases do we need? One. Okay, we need one basis element to complete our basis for R3. And what will our basis be for the orthogonal complement of R? What vector completes the basis for R3? 0, 1, 0. So our orthogonal complement is the span of 0, 1, 0, right? And we can verify that this vector here is orthogonal to every vector in R, right? If we take any scaled version of this and we take the inner product with any scaled vector from this subspace, we'll find that it's equal to 0. What this also means is that we can uniquely construct any vector in R3 as a linear combination of some set of vectors from R and some set of vectors from the orthogonal complement of R. This is kind of an intuitive example of an orthogonal complement. I know I've been saying a lot of kind of abstract math. Are there any questions on this notion of the orthogonal complement? Yeah, it's something that you need to just spend a little time thinking about, and it'll start kind of sinking in. I'm going to go through another example of finding an orthogonal complement that's not as easy. Okay, so let's look at a more challenging example. Okay, so let's find the orthogonal complement of the following subspace R in R4. Okay, so we have that our subspace R is equal to the span of the following two basis vectors, 1, 1, 0, 0, and 1, 0, negative 1, 3. Okay, so we want to find our complement. So first of all, how many basis vectors are going to be in our complement? 2, right? How do we know that? Right, because so R4, how many bases do we need to get to represent any vector in R4? We need 4 bases, which means our orthogonal complement has to contain 2 basis vectors. Okay, so how can we go about finding the orthogonal complement of this set of vectors? We have to find the set of vectors that are orthogonal to both of these. So how can we do that? Have to find all of the vectors that are orthogonal to these two. Exactly. So one way we can solve this is for each of these basis vectors, we take its dot product with some vector, we'll just call it x1, x2, x3, x4. We need to find what those elements are. And we have to have that this dot product is equal to 0. Similarly, we have that the dot product of 1, 0, -1, 3 with this set of vectors x1, x2, x3, x4 also has to be equal to 0. So that's the basic idea. We can do this by setting this up as a system of equations. Okay, so we take these two equations and we put them together. So let's say we now have a matrix equation 1, 1, 0, 0, 1, 0, -1, 3, multiplied by some vector x1, x2, x3, x4 is equal to the 0 vector. Okay, so what we're trying to do is we're trying to find the values of x1, x2, x3, x4 such that this system of equations holds. Okay, and in doing so, we'll be able to find the orthogonal complement of our original subspace R. Okay, so there's many ways to solve this problem. I'll give you kind of a systematic way of solving this problem. You can just do this by inspection for smaller problems, but I think perhaps the easiest way is to first put the system into reduced row echelon form, which you may remember from undergraduate. So I'm going to say put in reduced row echelon form. So we're going to apply row operations to transform this system into a form that's easier to work with. So we have x1, x2, x3, x4. It's equal to 0, 0. Okay, so if we take R2 and we subtract R1 from it and multiply by -1, we can put the second row in the form 0, 1, 1, -3. Okay, so this is R2 minus R1 times -1. And now we can subtract R2 from R1. So R1 minus R2, and we should get 1, yep. So it'll be 1, 0, -1, 3. Okay, so this is in reduced row echelon form, where we now have 2 pivot columns. So these are called pivots. They have a 1 in the leading entry and a 0 everywhere above and below. And then these 2 columns here, these represent our free variables. Yes. Did I make a mistake here? So R2 minus R1. So this will first be -1. And then we multiplied the entire second row by -1, right? Mm-hmm. I think I actually meant plus. No. Did I make a mistake here? All right, let's just check here and make sure I didn't make a mistake. R2 minus R1, so this will be 0, -1, -1, 3. Multiplied by -1 will be 1, 1, -3, right? And then subtract from the first row, this one will become 1, 0, -1, 3. Cool. So this should be correct. Okay. Thanks for checking though, because I do want to make sure I don't have any mistakes in my my lecture notes. Okay, so we have our system in reduced row echelon form. So now what we can do is we can write out the system of equations here. So we can look at this as a system of equations. So we have that x1 minus x3 plus 3x4 is equal to 0, right? That's from this first row. In the second row, we have x2 plus x3 minus 3x4 is equal to 0. So we can just rearrange this. So we can put x1 and x2 on the left-hand side by itself. And what we'll end up with is, sorry if I'm going a bit fast here, x1 is equal to x3 minus 3x4, and x2 is equal to negative x3 plus 3x4. All right. So now we need to find the values of x1, x2, x3, and x4 that satisfy this system of equations. Okay, so we have from this equation here that x1 is equal to x3 minus 3x4. And we have that x2 is equal to negative x3 plus 3x4. And because x3 and x4 are free variables, we can just write this as x3, x4. All right. So we can take this now and represent it as a linear combination of two vectors. So if we take this and separate it out, we'll get that this vector here is equal to x3 times some vector plus x4 times some vector. Okay, so really what we're saying is x1, x2, x3, x4. The set of vectors that complete our vector space, our orthogonal complement, is the set of vectors consisting of some scalar x3 times some vector plus some scalar x4 times some vector. So to satisfy the system of equations, what does this vector here have to be?
1 minus 1, 1, 0.
Yes, so this will be 1 minus 1, 1, 0. We can see that just if we look at this vector here, we have x3 minus x3, x3. So the first three elements will be 1 minus 1, 1. Okay, similarly for x4, we have that this has to be equal to negative 3, 3, 0, 1. And so these vectors here are the set of vectors from our original system of equations that are orthogonal to every element of R. Okay, so these two vectors here, this is a basis for our complement. So we can write that our complement is equal to the span of these two vectors, 1, negative 1, 1, 0, and negative 3, 3, 0, 1. And that is how you find the orthogonal complement of a subspace. Okay, and you can verify that these two vectors are orthogonal to every element of our original vector set. So if we go back, we had 1, 1, 0, 1, 1, 0, 0. If we take the inner product of 1, 1, 0, 0 with the first basis, we'll get inner product of 1, 1, 0, 0 with 1, negative 1, 1, 0. And we can see that this is going to be equal to 0. Similarly, if we take the inner product of 1, 1, 0, 0 with negative 3, 3, 0, 1, we'll see that it'll also give us 0. Okay, so these two vectors are orthogonal to every element in our original vector set, and they complete a basis for R4. Right. Are there any questions on this process before I move on? Any questions? There's numerical methods you could use to find the orthogonal complement. Also, one important thing to note here is that the bases that we found are not orthonormal. Okay, so generally we'll want to find bases that are orthonormal. Our original set of vectors was not orthonormal. And they're also not orthogonal to one another, right? So what you can do if you want to create a full set of vectors is use what's called Gram-Schmidt orthonormalization. And I have a section in the course packet about how to basically compute a full basis of orthonormal vectors. Why do I have such a hard time saying that word? Orthonormal vectors for a vector space, including including the subspace you're interested in and the orthogonal complement. So I'd say consult notes for algorithm for Gram-Schmidt. Gram-Schmidt orthonormalization.
You said that so they're not orthonormal, but you said they're not orthogonal even.
So our original two vectors in R, those are not orthogonal. Because if you take 1 times 1 is 1, plus 1 times 0 is 0, plus 0, so it'll have, they're not orthogonal to one another.
Okay.
So sometimes it's important to construct a basis for a subspace or a vector space that is orthonormal. And there's an algorithm for doing that, which is in the course packet. Yes. Okay. Great. Okay. Are there any questions on anything I presented so far? All right. Cool. So with that, what I'm going to talk about for the rest of lecture today is kind of fundamental. I'm going to talk about linear transformations, what they are, what they mean, and I'm specifically going to show how we could represent any linear transformation as a matrix. So this is for any linear transformation or any linear operator. We can represent it as a matrix. So first, let's define what I mean by linear transformation. It should be something that's familiar by this point, but let's define it formally. So a linear transformation, let's say we have vector spaces V and W. So let V and W be vector spaces defined over a field F. Okay. Then we can define a linear transformation, which I'll call L. This is a mapping from V to W. So it takes vectors from V and it maps them to some vector in W. We say that the transformation L is a linear transformation if and only if, and you can probably guess what I'm going to show. It's a linear transformation if and only if the linear transformation applied to alpha V1 plus beta V2 is equal to, what do you think? right? So alpha times L applied to V1 plus beta times the linear operator applied to V2 for all alpha beta in our fields and for all V1, V2 in our vector space V. Okay, so this is just the definition of superposition that we've been working with since the beginning of class, except we're applying it now specifically to vector spaces. In particular here, I want to point out that we have special names for the vector space V and W. So V, we refer to as the domain. It is the domain of the transformation L. And W is the codomain. So these pieces of terminology are important. These basically correspond to the idea of a domain that you learned in algebra, going all the way back when you first learned it. Basically, V is the set of vectors from which you are taking to apply the linear transformation to, and the codomain is the set of vectors that you reach by applying that linear transformation. Actually, I shouldn't say that. I should say that the codomain is the vector space onto which the linear transformation maps. But as we'll see a little bit later on, the linear transformation won't necessarily be able to map to every vector in that codomain. Okay, so we'll talk a little bit about those subtleties later. Okay, so let's give a couple examples of linear transformations. So some examples of linear transformations. Okay, first, just any sort of linear combination, right? Linear combinations. Differentiation. Integration. What are some other linear transformations that we know from this class? Sorry? So we'll talk about that. So I'll put that in parentheses. So a matrix, what we're going to show today is that, well, I'll spoil you. Any linear transformation can be represented by a matrix, no matter what it is. What are some other examples of linear transformations that we looked at in this class? Laplace transform. What's another one that's related to the Laplace transform? Sorry? Okay. Inverse as well. Fourier transform. What about another operation we talked about in class quite a bit? It's on homework 5. Convolution. Okay. The trace of a matrix is a linear operator. So there's a lot of different types of linear transformations that we've encountered in class. What I'm going to show you next is that any of these linear transformations can be represented by a matrix, which we'll call A. And fundamentally, this is what a matrix is. This is what a matrix is doing, is it is applying a linear transformation in some basis. So let's go through this proof. I'm going to show you that any linear transformation can be represented by a matrix in some appropriate basis. Okay, so I'll take this a bit slow because it can be a bit subtle. The reason it can be a bit subtle. So let's say we have a linear transformation L. So we'll say let L be a linear transformation from a vector space V to W. So in other words, L is a mapping that takes us from V to W. And let the following collection of vectors, V1, V2 through Vn, be a basis for V, and W1, W2 through Wm be a basis for W. So in other words, let this set of vectors V and this set of vectors W be bases for our vector spaces V and W respectively. Okay. So with this being true, the action of L on one of the bases of V is necessarily some linear combination of the bases of W. In other words, if we apply our linear transformation to one of the bases elements of our domain, that's equal to some linear combination of the basis vectors of W. So alpha 1, W1 plus alpha 2, W2, and so on, all the way to alpha M, WM. So why is this true? Why is this true? Why is it that if we apply our linear transformation to one of the basis vectors of V, that it has to be some linear combination of the basis vectors from W? Exactly. So if our linear transformation maps to the codomain W, we have to be able to represent that vector that it maps to with the bases of W because it lies within W. Okay. So we know that our linear operator applied to one of the basis elements of V has to be some linear combination of the elements of W. So we can write this as a matrix vector product. So there's just one linear transformation, just one L. And when I'm saying LV1, really this is saying L applied to V. Oh, this is alpha. Yeah, this is alpha. So this is just some scalar. Yeah, sorry. This is just some scalar. Okay, so it's some linear combination of the bases of W. Okay, we can also write this using our definition of the matrix vector product as some matrix W and some vector alpha. Okay, where W is just the bases of our codomain stacked together. So we have W1 through WI through WM all stacked together. And we have alpha, a vector equal to alpha 1, alpha 2, and so on, all the way through alpha M. Okay, and this just follows from our definition of the matrix vector product. If we take W and we apply the product of W alpha, it gives us this expression here. And this just follows from our definition of the matrix vector product. All right, okay. So we have this set of alpha coefficients for one of the bases. What we can say now is that we can define a set of alphas for each of those bases of V. Okay, so we can define a set of alphas for V1. We can define a set of alphas for V2. We can define a set of alphas all the way up to Vn as in November for all of the bases of V. And we can say that we can define a matrix representation of L. Okay, so we have a matrix representation A, where the columns I'll call A1 through AI through AN. Where the action of L on each basis of V, Vi, is represented by the ith column of A. Okay. Where the action of L on Vi, the ith basis of our domain, is represented by the ith column of A. Okay, so let me write this out. This is probably the hardest part to follow here. We have that the action of L on any of our bases Vi is equal to A1I times W1 plus A 2I W2 and so on all the way to A MI WM. And we can represent this again as a matrix vector product as WAI. Okay, so what happened here? What was the step? So from before, we showed that the action of our linear operator on the basis Vi was given by this linear combination of the bases of our codomain, right? Where we have some set of alphas. So basically all I'm saying here is that we can take that set of alphas for Vi and stack them as one of the columns in a matrix. And we can do that for each Vi. We can do that for each element of our domain, each basis element of our domain. So all we're doing is we're finding those alphas for each one of Vi, and we're just stacking them up into a matrix A. Okay, so we've just defined this matrix A as that definition. Okay. All right. Okay, so we've got that the action of our linear operator on one of the bases of our domain is equal to some matrix W, which represents the basis of our codomain, times the ith column of our matrix A. Okay. Now let's look at the action of our linear operator on just some vector from our domain. Okay. We can show that the action of L on a vector U from our domain V is uniquely determined by its action on the basis of V. In other words, we can say that any vector U from our domain has to be represented by some linear combination of the basis elements of our domain. Okay, up through Xn, Vn. Okay. We can represent this again as a matrix vector product, V times X. Okay, where X is just some vector of coefficients. So basically, we have that any vector in our domain is represented as a linear combination of the elements of our basis of our domain. And therefore, if we apply our linear operator to any element in our domain, it's equivalent to applying that linear operator to the scaled elements of our basis. Okay, so we can write that the action of L on U, the action of L on U is given by L applied to U, which is just some arbitrary vector in our domain. We know that this is equal to L applied to Vx, where V is the stacked matrix consisting of our vectors of our domain, and X is just some set of coordinates. Okay, we have that this is equal to X1 times the linear operator applied to V1 plus X2 applied to the linear operator applied to V2, and so on all the way to Xn times the linear operator applied to Vn. All right. Now we can do something using the knowledge that we've gained before. Okay, what is L applied to V1? We have that L applied to V1. So for VI, this was equal to W times AI. So in this case, it'll be W times A1. So this will be X1 W times A1 plus X2 W times A2, so on all the way to Xn W times AN. Okay, and if we factor this out, we can write this using our definition of the matrix vector product as W, our matrix of the bases of the codomain, times our matrix A times X. Okay, so we have that our linear operator applied to Vx is equal to W times our matrix representation of our linear operator A times X. And in this case, because U and X were arbitrary, we have that our linear operator applied to V is equal to W times A. Okay, so just to finish this thought, if W and V are in the standard basis, so if we are operating in the standard basis, W and V are both equal to I, and then our linear operator L is simply equal to A. Okay, so what this goes to show is that any linear operator L, no matter what it is, can be represented by a matrix A in an appropriate basis. Okay, so in this case, we normally have to account for both the basis V of our domain and the basis W of our codomain. But any linear operator, no matter what it is, can be represented as a matrix in an appropriate basis. All right. Are there any questions on this derivation? I know this is probably one of the most kind of subtle derivations we've done in this class, but it's an important concept to know. So let me go through a quick example of how we can represent a linear operator using a matrix. So this is a relatively straightforward example. On Thursday, we'll go through some examples that are a little less straightforward. Okay, so let's consider the linear transformation which I'll call A. I'll give it this kind of calligraphic A to distinguish it from our matrix A. That is a mapping from R3 to R2. Okay. Where our linear operator A operates on a set of coordinates x, y, z, and gives us back a vector where the first element is x plus z, and the second element is 2y minus z. So let's write this out using our equation from earlier. We have that our linear operator applied to Vx is equal to W times A times X. So let's label these just so we are familiar with what they are. So A, this is our linear, I'll call it just linear transformation. Okay, what is V? What is V? Sorry? Yeah, so this is the basis of the domain. Let me save some space here. It's the basis of the domain. What is W? Basis of codomain. And A is the matrix representation of the linear transformation. So I'll just write LT. X, in this case, is the coordinates in our basis that we're applying this operation to. Okay, so when we're talking about vectors, it consists of coordinates in a basis. That's important to remember. Okay, so let's write this out. I have 1 minute. All right, let's write this out. So we have A applied to, sorry. So our basis of our domain is, let's just write it in terms of the canonical basis. So 0, 1. So it's just the identity matrix in R3. Our coordinates, I'll just express as x, y, z. Okay, then we have W. So the basis of the codomain, what is our basis of our codomain then? Yeah, so it'll just be the identity matrix in R2. Then we have our matrix A, which I won't fill in yet. And we have our coordinates x, y, z. Keep on wanting to say x, y, z for some reason. I'll just go with it. Okay. And we have to have our matrix A defined such that when it's applied to x, y, z, we get this vector here. Okay. So what are the elements of A going to be? What's the first row of A going to be to represent our linear operator? Okay, so the first row here is going to be x plus z. So the first row of A needs to be 1, 0, 1, exactly. Okay. And you can see the second row of A will be 0 to -1. Okay, so this was a simple example of how we could represent a linear transformation using a matrix. On Thursday, we'll get into some more interesting examples, and we'll also start to look at some new concepts that you may not have seen yet, particularly the range of a linear transformation, the null space of a linear transformation, and we'll start talking about what are called the 4 fundamental subspaces, which is going to be important going forward for specifically looking at controllability and observability, but it has a lot of different uses aside from that. Okay, so with that, I will let you go. Have a great rest of your day, and I'll see you on Thursday.